All right, some quick notes over nuclear chemistry, radioactive decay. Got three particles, alpha, beta, and gamma. And so those are the most important. These other two over here, positron and electron capture, are very similar to some of the particles over here to the left, alpha, beta, gamma. So they're going to look kind of similar, and we're not going to spend a lot of time focusing in on those. So let's take a look specifically at alpha, beta, and gamma. So let's start with the alpha. Alpha has looks like this, 4 over 2 He, or a 4 over 2, and then the Greek A kind of looks like a fish. And so when you look at those, they're the same thing. So like I said, it's kind of like this fish, eye there, mouth there. So there you go. So there you go. That's the two symbols. Now they're the same exact thing, and so we want to look at charge and mass. And so kind of think about what we talked about with the periodic table, with the mass value kind of being up here, and that's this right here is basically the number of protons you have. So if you kind of think about it, the bottom number here is really your protons, and so if you have 2 protons, then that is a +2. And so that's kind of where the charge is going to come from, is going to be that number on the bottom, and then the mass is going to be the number on top. So if we look at it that way, then the charge for our alpha particles we're going to say is +2, and then the mass we're going to say is going to be 4, meaning that when you do problems with this, the mass will change by 4 and the charge can change by 2. And then down here, you can see there's some other concepts. Damage capacity. The damage capacity for the alpha we're going to say is low. So alpha particles are not particularly dangerous in terms of radiation. And what can you block them with? So this word penetration, or how much can they penetrate, we're talking about what can the particles go through. And so these can be blocked by a piece of paper, and so that kind of gives you an idea of how much they can penetrate. Not really, can't really penetrate that much. That's why they are not very dangerous. So you can put down here blocked, and I'm going to run out of space, but you guys can fit in blocked by paper. So just a piece of paper will block these alpha particles. Sample decay problem right here. We're going to look at this on the back, but it's really very easy. You need the top and the bottom to match up on both sides. So if you look on the left, it's 222, and the top on the right is 4 plus 218, which is also 222. And on the bottom, you can see it's a 2 plus 86 is 88. Well, there you go, 88. So basically, both sides have to be the same on the top and the bottom. So what I tell students is go ahead and look at this arrow. Kind of think of this arrow right here as an equal sign, meaning the left side equals the right side. There's alpha. So let's go ahead and clean this up. Give me a little more space so I can look at beta. So I'm going to clean up a few things here. So the beta particle is going to be quite a bit different, because it's going to have, it look like this, a 0 minus 1 E, or a 0 minus 1 and this Greek B. So when you look at the beta, that's what this is right here. This is the Greek beta. And so same concept. The mass is going to be associated with this top number, and then the charge is the bottom number. So like it's just kind of right there for you. So we're going to say that the charge on these is going to be -1, and we're going to say that the mass is going to be 0, meaning that the mass doesn't change during this type of decay. Okay, down here, damage capacity. What is the damage capacity? We're going to say that these are going to be medium. Okay, so these are going to be medium. Not really that concerning again, but they're in the medium range. And then what can they penetrate? The beta particles can penetrate or what can they be blocked by more than what can they penetrate? They can be blocked by heavy clothing. And so if you're wearing heavy clothing, jeans, denim, coveralls, things like that, they're going to block these particles. So they're going to be blocked by heavy clothing. And so then that's the idea of what you're wearing can basically protect you from these. Again, not concerning. And we'll say heavy clothes. There we go. All right. So that takes care of the beta. Again, I'm going to have to clean this up, give myself some space. And so you've got all the pieces there. So we're going to clean this up and I'm going to go over here and add in the gamma particle. Okay, so the gamma particle, mathematically, not going to do a lot. Probably should go back real quick and talk about the mathematics. It's the same thing. Left side equals right side on the beta. So if you look real quick, you can see I've got a 14 here on the top. And the left is 14 and 0. That also equals 14, so that's good. Left side equals right side. Okay, the bottom is going to be 6 on the left, and then 7 minus 1. So 7 minus 1 equals 6. A lot of times students don't register the minus 1, and so they can get this problem wrong. And so it's real simple. Just do exactly what it's saying. Take the number minus 1. Good to go. Now, I should point out that you can actually have multiple decays at once, so you don't always just have a single decay. You could have like 2 or 3 or 4, which could be a little more complicated. So, okay, gamma, right here, here's the symbol for the gamma. Never super great at drawing this, and so again, you got your Greek symbol, and so a lot of times we go 0, 0, and then we do the, again, not the best rendition of that, and so we'll try it again. And so here we go, a little bit better. Just the Y, the Greek Y symbol there for the gamma. Now notice 0 over 0. We are right here, if you look, double zeros means that this is not going to be having a change in charge nor a change in mass. This is just an energy change. And so it's not that it's unimportant, because the energy is important, as we'll see in a minute, but it's not going to change anything in terms of the actual nuclear or atomic symbol. So we can go ahead and just say that the charge is 0 and the mass is 0. So if you look down here, mathematically, it's not going to do anything to your nucleus. So if we look here, you can see, oh, 238 on top, 238 on bottom, 92, 92, because right here, this is all zeros, and so this is zeros, not going to be doing anything. Okay, let's talk about damage capacity and what it can penetrate. So these are gamma rays. These are the things that create superheroes. So, you know, like the Incredible Hulk, created by gamma rays. Spider-Man, created, you know, was bitten by a spider, affected by gamma rays. So it's all the same thing. The classic superheroes were all created from radiation, and so if we look at this, we want to say the damage capacity is high. If it can create a superhero, it is dangerous stuff. Now, what can it penetrate? Well, gamma rays are the dangerous things, the radiation we have to be most concerned about, and they can penetrate a lot of substances. So to block these chemicals, they're going to be blocked by concrete or heavy metals. So you're talking dense items. So you're blocked by dense items, specifically lead, so lead-lined containers, or concrete. So these are the items that can protect you from the more dangerous radiation. And so, like in Chernobyl, they've built the sarcophagus, which is just a big chunk of concrete on top of the damaged reactor to keep that radiation inside. So again, what blocks gamma rays? Dense items such as lead or concrete. Good thing to know for test or quiz. All right, so let's go down here. Positron, just going to point out, we're not going to spend a lot of time here, that the positron, if you look, it is a 0 minus 1 B, which looks suspiciously like the beta particle, right? So it's going to basically act in the same manner. I'm not going to spend a lot of time with that. And electron capture 0 minus 1e, again, looks suspiciously like a beta particle. Just some slight differences. I'm sorry, I wrote down my mistake. I wrote down the positron as a -1. That is a +1. And so what you can think of the positron is this is a slight change with a positive value on the atomic number. And when we look down here, we're going to see that we're going to have 15 and 0 is 15, good. 8 versus 7 plus 1, 7 plus 1 is 8. Now, the electron capture is going to be over here on the left side. So if you got your arrow here, electron capture is going to be a beta particle, but it's going to be on the left side of the equation or with the reactants. And so we're going to have over here on the left side or with our reactants, that's where you're going to find the electron capture. Now, the positrons, again, just basically the opposite of the beta decay. And so just a slight variation. So we're not going to spend a ton of time with those. Just you be able to do the math, which you'll be able to do because it's very, very straightforward. Okay, try and get through this quickly. Let's slide down here and let's take a look at the fission and fusion. So real quick, fission definition you need to know versus fusion. Fission is going to be if we are going to split the nucleus. And you can see here we are splitting over here on the right. So this uranium here is splitting. So right here it's splitting, and you can see it breaks into a barium particle, a krypton particle, and some neutrons. And then over here, this is the concept of a chain reaction, which is like dominoes. So like you have one domino, and then it goes ahead and it knocks down 2 dominoes, and then of course this domino is going to knock down 2 more, and this one is going to knock down 2 more, and they just keep going. And so you get this idea of a chain reaction. So set up 10,000 dominoes, knock one over, one knocks over 2, 2 knock over 4, exponentially they grow, and you just knock over lots of dominoes. That's a chain reaction. And so if you let a chain reaction go, you're creating like a nuclear weapon. If you contain a chain reaction, you are creating a nuclear reactor. Okay, down here real quick, fission is combining. This is going to be, we're going to combine 2 nuclei. So we are going to put them together. That's the idea of fusion. And if you combine 2 of them, that will also create energy. Fantastic way to create energy. No radiation, but very difficult to do in theory. I'm going to quickly go through some examples with you right here of just how to do the decay. And so left side equals right side. So think of this as an equal sign. So right here, 242. That's a 4, so this top number needs to be 238. 238 plus 4 is 242. Bottom number needs to be a 92. 92 plus 2 is going to be 94. Now, if you look here, we have changed our element. And the new element, we look it up, number 92 is uranium. So there we go. There's our decay. So next one here, 32 on top and 0 is 32. So these add up to 32. And 16 minus 1 is 15. Look it up on the periodic table, number 15, and you've got phosphorus. Okay, next one, you got some californium. And then this is a multiplier of times 3. So we actually have 3 neutrons. And so we're going to have 3 plus 259. So you're going to have 262. So this left side is going to need to be 10. And then right here, 3 times 0 is 0. So bottom is going to be 103. And so then we've got 98 and 103. So 5. So we look up element 5 and you get boron. Okay, only a few seconds left on my recording, so I'm going to stop here, but you get the idea. Left side equals right side.